All right. Let's have a look at Matrices Two. So this is the second half of the lesson, matrices. Um, at the end of this part of the lesson, you should be equipped to at least attempt the questions in the homework. Now, the determinant of a 2 by 2 matrix. So, um, first of all, we'll start out by saying that if A is the matrix, if A is the matrix A, B, C, D, this would be the symbol for the determinant of A. That would be the symbol for the determinant of A. Now, the determinant of A would be equal to um, A times D. So it's A times D. So it's A times D, which would be AD, minus B minus B times C, which would be what? BC. So the determinant of A would be A times what? D. So you multiply the two diagonal elements, the two leading diagonal elements, minus the product of the two lagging diagonal elements. All right. Now, if the determinant of a matrix is equal to 0, the matrix is a singular matrix. And if the determinant is not equal to 0, the matrix is a non-singular matrix. So a singular matrix is a matrix in which the determinant is equal to 0. And a non-singular matrix is a matrix in which the determinant is not equal to 0. Let's have a look at an example. It says, given that A is a singular matrix, determine the value of P. All right. Now, if A is a singular matrix, so we're told in this example that A is a singular matrix, and A is a singular matrix means that the determinant of A is equal to 0. Let us find the determinant of A. So the determinant of A would be equal to 6 times 6, which is 36, minus, all right, so let's sort of spell it out. It's 6 times 6 minus 4p times p. That's 4p times p. That would be the determinant. Now, because A is singular, this determinant is equal to 0. So what we have is 36 minus 4p squared is equal to 0. So 36 would be equal to 4p squared. All right. So negative 4p squared goes over and become positive. If I divide both sides of the equation by 4, I'm going to get p squared is equal to 9. The opposite of square is square root. So p would be equal to the square root of 9. P would be equal to positive or negative 3. All right. So if the matrix A is singular, the value of P is either positive 3 or negative 3. Inverse of a 2 by 2 matrix. Now, this would be the symbol for A inverse. A. That would be the symbol for A inverse, and A inverse is equal to 1 over the determinant of A times A adjoint. That is 1 over the determinant of A times adjoint A. All right. So let's have a go. Now, in this example, we're given the matrix A and we're asked to find A inverse. A inverse is equal to 1 over the determinant of A times adjoint A. Now, so let's find the determinant of A. The determinant of A would be equal to 1 times 3. So that's 1 times 3 minus 5 times 2. So this would have been 3 um, minus 10, and 3 minus 10 would be equal to 13. So the determinant of A is 13. Now, therefore, A inverse would be equal to 1 over 13 times adjoint A. Now, what would be adjoint A? Adjoint A, to find adjoint A, we're going to switch around the diagonal elements, switch around the leading diagonal elements, that is A and C. In this case, the leading diagonal elements is 1 and 3. We're going to switch them around. So this is 3 here and 1 here. The other two elements stay in place. The other two elements stay in place, but their signs change. So minus 5 becomes positive 5, and positive 2 becomes negative 2. All right. So so now we're multiplying this matrix by 1 over 13. Multiplying by 1 over 13 is the same as dividing by 1 over 13. Dividing by 13, sorry. So A inverse would be 3 over 13, 5 over 13, minus 2 over 13, and 1 over 13. This is A inverse. Earlier we mentioned the adjoint matrix. I didn't think that would quite explain it, so let me just have a look at it again. All right, so this is actually A inverse. This is A inverse. All right, but if A is the matrix, let's say A, B, C, D, adjoint A, or A adjoint would be equal to, all right, here's what we do. To find adjoint matrix, you're going to switch around the leading diagonal elements, which is A and D. And this is so D comes up here and A comes up here. The other two elements, B and C, stay in place, but their signs change. So this is minus B minus C. So to find the adjoint matrix, you switch around the two leading diagonal elements. The other two elements, B and C, stay in place, but their signs change. All right. This says A inverse. A times A inverse is equal to A inverse times A, which is equal to I. So that note is basically saying to us that if we multiply a matrix by its inverse, we're going to get the I matrix. If we multiply a matrix by its inverse, we're going to get the I matrix. Earlier, or in matrix 1, we saw that A times I is equal to A. And now we're learning that A times A inverse is equal to I. All right. So those are two matrices identities which are important. All right. So here's an example. We're told that A is that matrix 1, 3, minus 2, minus 4. We're to show that A times A inverse is equal to A inverse times A is equal to I. All right. So let us find A inverse. A inverse would be equal to 1 over the determinant of A times adjoint A. Now, the determinant of A would be 1 times minus 4, which is minus 4, minus 2 times 3, which is what? 6. So this is minus 4 plus 6, and negative times a negative is a positive, or minus is plus. So the determinant here would be equal to 2. Therefore, A inverse would be equal to 1 over the determinant, which is 2, times adjoint A. Now, adjoint A would be, you're going to switch around the diagonal elements in A, the leading diagonal elements. So this is minus 4, 1. These two elements change position. The other two elements stay where they are, but their signs change. Negative 2 becomes positive 2, and positive 3 becomes negative 3. All right. So we're going to keep A inverse in this form. We're not going to multiply the elements by the half. All right, because it's easier to multiply multiply the matrices when it's in this format. Multiply A by A inverse when A inverse is in this form. So let us find out what is A times A inverse. All right. So we're asked to show that A times A inverse is I. So let's multiply A by A inverse. So we're going to multiply A by A inverse. A is the matrix 1, 3, minus 2, minus 4. And A inverse is the matrix minus 4, minus 3, 2, 1. And then lastly, we must multiply by a half. So let's multiply the two matrices first. Remember when you multiply two matrices, 1, 2, 1, 2, you multiply a row by a column. And to multiply a row by a column, it's the first element in the row, first element in the column, second element in the row, second element in the column. So 1 times minus 4 is minus 4. Minus 2 times minus 3 is positive 6. All right, so let's multiply the top row by the left column. Now we're going to multiply the top row by the right column. All right, so I'm identifying the first element in the column and the second element in the column. So it's 1 times 2, which is 2. 1 times 2, which is 2. And minus 2 times 1, which is minus 2. But the half here at the end, because when we finish multiplying the two matrices, we have to multiply by the half. So let's go down now to the bottom row. And so it's bottom row and left column. So 1, 2, 1, 2, 1, 2. So again, you all should have practiced this and know it by now. When you're multiplying two matrices, you multiply what? The rows of the first matrix by the columns of the second matrix. When you, every time you multiply a row by a column, you get an element in the answer. If you multiply the bottom row by the left column, you're going to get the bottom left answer. When you multiply a row by a column, it's the first element in the row multiplied by the first element in the column plus the second element in the row multiplied by the second element in the column. So 3 times minus 4 is minus 12. Minus 4 times minus 3 is positive 12. All right, so let's multiply the bottom row by the left column. I'm going to multiply the bottom row by the right column. 3 times 2 is 6. Minus 4 times 1 is minus 4. So what we end up with is, let's bring back the half at the front, a half. Then we have 2, 0, 0, 2. A half of 2 is 1. A half of 0 is 0. A half of 0 is 0. A half of 2 is 1. So we multiplied A times A inverse, and what we got is the I matrix. So A times A inverse is equal to I. We're asked to show that, and we just did. But let's do the other side, and I'm guessing the other side basically is going to come out to be the same. That this is also true, that A inverse times A is equal to I. All right, so remember these two identities. I said that they're going to come in. They're going to come in handy very shortly. So if you multiply a matrix by the identity matrix, you get back the matrix. And if you multiply a matrix by its inverse, you get the I matrix. All right, solving a matrix equation of the form AX is equal to B, where A, B, and X are matrices, and X is an unknown. All right, so we're looking at how do we go about solving a matrix equation. All right, so or how do we go about solving a matrix equation of the form AX is equal to B, where A, B, and X are matrices, and X is an unknown. Let's change the color here a little bit for emphasis. All right, these are the two principles, or the two identities, which are going to help us to solve this matrix equation. A times A inverse is equal to A inverse times A is equal to I. We just show that yes, that is true. And I times B is equal to B. I times A is equal to A. If you multiply a matrix by the identity matrix, you're going to get back the original matrix. All right. Um, Now, here we want to solve, this is a matrix equation. It's not a regular equation, so you can't just divide by A to solve. It's a matrix equation, A, B, and X. A, X, and B are matrices. X is the unknown. All right, so what I want to do is that I want to get rid of the A from the left-hand side so that all that I'm left it is the X. All right, because if you solve an equation for X when you finish, you must have X alone on one side. Now, to get rid of A, I'm going to multiply, to get rid of the A, I'm going to multiply A by A inverse. So I'm going to multiply both sides of the equation by A inverse. So now we're going to have A inverse times A X is equal to A inverse times B. Remember, my objective is to get rid of the A altogether. But from principle one, if you multiply a matrix by its inverse, you get the I matrix. So this is IX is equal to A inverse times B. Principle two says that if you multiply a matrix by the I matrix, you get back the matrix. So if I multiply X by I, I'm going to get back what? X. So X is equal to A inverse times B. Therefore, that is basically how you would go about solving the matrix equation of the form AX is equal to B, where X is an unknown. Therefore, to solve a matrix equation of the form AX is equal to B, simply write back X and multiply the right hand side by A inverse. All right, so in a sense, essentially, what we're doing is that in solving a matrix equation of the form AX is equal to B, we're basically going to jump these two steps. Basically, going to jump these two steps. All right, we're basically going to jump those two steps and go straight from what? One, straight from here to here. So to why are we saying that? Because we know that this is going to happen. If you know it's going to happen, you don't need to do it. Just move straight from this step here at the top to straight to the step at the bottom. Therefore, to solve a matrix equation of the form AX is equal to B, where AX and B are matrices and X is an unknown, we simply write back X and multiply the right hand side by A inverse. All right, a fact that in the next step is going to come in very handy. All right, so this is actually, I think, the absolute last thing in the topic. Solving a pair of simultaneous equation using a matrices method. All right. So the example says solve the following pair of simultaneous equation using a matrices method. All right. The first thing we're going to do is we're going to write the simultaneous equation, the pair of simultaneous equation as a single matrix equation. So I'm going to take the what? The coefficient of all the terms on the left. So let's change the color. The coefficient of x here is 1, of 3x at the bottom is 3, of y is minus 2, and of y at the bottom it's 1. So then now I'm just going to put x and y here, and this on the right you have minus 4 and 9. All right, so I didn't introduce anything new. The first matrix is basically it's called, I think, the coefficient matrix. And basically how I got it, I simply took the coefficients of x and y to form it. Now this matrix is therefore of the form AX is equal to B. Now a while ago we learned that to solve a matrix of the form AX is equal to B, we simply write back X and multiply the right hand side by A inverse. So very important to the solution is A inverse. Now A inverse is equal to 1 over the determinant of A times adjoint A. Now the determinant of A is equal to 1 times 1, 1 times 1, which is 1, minus 2 times 3. So multiply by those two. Minus 2 times 3, which is minus 6. All right. So the determinant is going to be 1 plus 6, which is 7. So A inverse is 1 over 7 times adjoint A. Remember, for adjoint A, we're going to switch around the diagonal elements, or the leading diagonal elements. So if you switch around 1 and 1, you still get back 1 and 1. The other two elements stay in place, but their signs change. So minus 2 change to positive 2, and positive 3 changes to negative 3. All right, and we're going to keep A inverse in this form. Now, therefore, as I said, write back X. X is what? XY is equal to B times A inverse. So you write back X and multiply the right hand side by A inverse. This is 1 minus 3, 2, 1 times B, which is what? Minus 4, 9. Let's multiply the two matrices and then multiply by the fraction last. 1, 2, 1, 2. 1 times minus 4 is minus 4. 2 times 9 is 18. Alright, so let's move down now to the bottom row. We're multiplying 2 rows, but only 1 column. 1, 2. So minus 3 times minus 4 is 12. And 1 times 9 is 9. So therefore, what we have is what? X, Y will be equal to 1, 7. Alright, I'm sure that this should have been 18. 1 times minus 4, 2 times 9 is 18. So minus 4 plus 18 is 14. And 12 plus 9 is 21. Therefore, X, Y, 7 into 14 is 2. 7 into 21 is 3. So the matrix XY is equal to the matrix 2, 3. Therefore, X is equal to 2 and Y is equal to 3 are the solutions of the simultaneous equations. Alright guys, this is the end of matrices. I've already sent you the homework already. So what I need for you to do now is get practicing. If there's anything else in the homework that you're not quite clear of, what you simply do is just go back to the video, look for the section of the video that talks about that. For clarity. All right.